Welcome to aminacademy.com. In electrical engineering, let us discuss about electric potential and potential difference. We know that a body raised above the ground level has a certain amount of mechanical potential energy, which by definition is given by the amount of work done in raising it to that height. If, for example, suppose a body of mass 10 kg is raised against the gravity through 9.8 meter, then the potential energy is 10 into 9.8, that is 98 meter kg, then which is called that much joules. The body falls because there is an attraction due to gravity and always proceeds from the place of higher potential energy to one of the lower potential energy, that is a ground. So we speak about a gravitational potential energy, or briefly potential, at different points in the Earth's gravitational field. Now consider an electric field. Imagine an isolated potential Q. Suppose here isolated potential Q. Suppose this is isolated potential Q. The point A is this, then point charge plus charge at x distance. Now consider an electric field. Imagine an isolated positive potential charge Q placed in air. Like its gravitational field, it has its own electrostatic field, which theoretically extends up to infinity. If the charge x is very far away from Q, say that infinity, then force on it's practically zero. That regarding the potential, regarding the charge, point charge Q, here very large distance, so here there is no effect. As x is brought nearer to Q, suppose you want to come nearer to Q, a force of repulsion acts on it because positive and positive repulse each other. Hence, work or energy is required to bring it to a point like in the electric field. Hence, when a point A, charge X has some amount of electric potential energy. Now we'll define further. Electric potential, that is the amount of work needed to move a unit charge from a reference point to a specific point against the electric field. Typically, the reference point is Earth. Although any point beyond the influence of the electric field charge can be used electric potential. Now further explanation of electric potential. The amount of work needed to move a unit charge from a reference point to a specific point against the electric field. Typically, the reference point is Earth. Although any point beyond the influence of the electric field charge can be used. That means our reference point is Earth. From that, we calculate the potential energy. The diagram shows the forces acting on a positive charge Q located between two plates A and B of an electric field E. The electric force F exerted by the field on the positive charge F equal to QE. To move the charge from plate A to plate B, an equal and opposite force, that is F dash equal minus QE, must then applied. The work W done is moving the positive charge through a distance of D is W equal F dash D, which is equal minus QED. This is a potential difference. The potential energy for a positive charge increases when it moves against an electric field and decreases when it moves with the electric field. The opposite is true also. Unless the unit charge crosses the beginning changing magnetic field, its potential at any given point does not depend on the path taken. This for magnetic field, we'll discuss later. Although the concept of electric potential is useful in understanding electrical phenomena, only difference in potential energy are measurable. If an electric field is defined as the force per unit charge, then by analogy, an electric potential can be brought off as the potential energy per unit charge. Now look at electric potential energy. Here two places having positive charge and negative charge. What is the potential energy now? Electric potential energy is the energy that is needed to move a charge against an electric field. Electric field, we need more energy to move a charge further in the electric field, but also more energy to move it through a stronger electric field. Suppose electric field is stronger, we need more energy to move a charge, positive charge between the plates. Next, next we'll discuss about potential difference. Between any 2 points in the electric field is defined as the amount of work done in moving a unit positive charge without acceleration from one point to another along any path between 2 points. Here, this is voltage versus potential difference. So it tried to move the charges from lower potential to higher potential, or from higher potential to lower potential regarding the voltage terminals. Therefore 1 volt potential difference is nothing but 1 joule of work divided by 1 coulomb of charge. That is, volt is J by Q, joules per coulomb. Now we'll discuss about electric potential at a point is equal to a work done by external force in bringing the unit positive charge from infinity to a point inside the electric field without changing the kinetic energy. Look at here, V equal to KQ by R, which is equal K is 1 by 4 pi epsilon 0 R. Therefore, V is Q by 4 pi epsilon 0 R. That is the charge Q, the distance R is the radius of the sphere. Now we can find work done, that is dW is equal Q over 4 pi epsilon 0 R square minus dx. Now therefore we can find work by integrating this function with respect to x is infinity to the x is the point D, that is Q into dx, that minus you are taking out, over 4 pi epsilon 0 x square. Now integrating within the limits, we can get Q minus 4 pi epsilon 0 is the constant taken out, infinity to point D of dx by x square, which is further minus Q over 4 pi epsilon 0 minus 1 over x, because here 1 over x squared integration is minus 1 over x, infinity to point D equal minus Q over 4 pi epsilon 0. We are giving the limits D and infinity, that is minus 1 over d minus or minus 1 over infinity equal, after simplifying we get q1 over infinity is 0, therefore second limit is become 0, therefore 4 pi epsilon 0 d joules. Therefore work done is q over 4 pi epsilon 0 d joules. Now potential in charged conducting sphere. The use of Gauss law to examine the electric field of a charged sphere shows that the electric field environment outside the sphere is identical to that of the point charge. Therefore, the potential is the same as that of V equal to QQ over R, that is Q, R is 1 over 4 pi epsilon 0 R. Now, the electric field inside a conducting sphere is 0. So, the potential remains constant at the value it reached at the surface. That is V inside equal to AQ over R. R is the radius of the sphere. That is Q over 4 pi epsilon 0 R. This is a V inside. Now, we will discuss about EQ potential surfaces. The surface, the locus of all points at the same potential is equipotential, is known as the equipotential surface. That means everywhere that surface, that potential difference is same. Potential is same. No work is required. No work is required to move a charge from one point to another on the equipotential surface. In other words, any surface with the same electric potential at every point is termed as an equipotential surfaces. Here, electric field inside and conducting sphere. According to Gauss law, the electric field inside a conducting sphere is always zero irrespective of how much charge resides on its surface. Due to zero electric field inside the sphere, the electric flux inside a sphere is zero. Here, the outside electric potential, the electric field equal 1 by 4 pi epsilon 0 q over r square when r is greater than radius of the sphere, that is very far away from, that is outside of the sphere. On the sphere is 1 E vector equal to 1 over 4 pi epsilon 0 q over capital R square, because we are substituting radius r. Then r equal to r. This is on the sphere. Inside the sphere, if E vector is 1 over epsilon 0 q over, that is here after integrating become r cube, where r is very less than r. If r is 0, that is at center, it becomes 0. What is potential gradient next? According to the definition, the potential gradient is the potential difference, that is decrease in potential from high potential end divided by the wire's length. It represents the slope along which the potential is changing. In other words, the potential difference per unit length is the potential gradient. Here, this is a higher potential. That means some charge falls from higher potential to lower potential. Here, the distance of the wire. So, this divided by this. That means the gradient. Potential gradient. Potential gradient is the potential difference, that decrease in potential from high potential end divided by the wire length. Next is dielectric strength. Is measured as the maximum voltage required to produce a dielectric breakdown through a material. Suppose two wire, that is end to end, not connected, means if between that voltage is higher and higher, very high, then it breaks the air, that is dielectric, and spark will come between two ends, two terminals. So it is a potential dielectric strength breakdown. It is expressed as a volts per unit thickness. For a plastic material, the dielectric strength varies from 1 to 1000 megavolt per meter. That much higher resistance, that higher potential break energy we need to break the potential strength, dielectric strength. Higher dielectric strength corresponds to a better insulation properties. Look at here. These are some graphical relations between dielectric constant and breakdown field. Breakdown of field is this much voltage is higher when dielectric constant goes like that. So far we discussed about different terms of electric field. We have done. Please subscribe our YouTube channel.